Welcome to Summarize Science, where we dive into the latest breakthroughs in AI research. Today, we are looking at a paper that addresses a major hurdle in how computers learn to generate complex images. The researchers introduce a new method called Posterior-Augmented Flow Matching, or PAFM for short. To understand this, first we need to look at standard flow matching, which acts like a guide for AI to transform noise into a clear picture. Usually, these models are trained by following a single path between a starting point and a final image. However, for high-dimensional data like photos, this single-path approach is often too sparse for the AI to learn effectively. This can lead to a problem called flow collapse, where the AI memorizes specific pairs instead of learning the general logic. Essentially, the computer gets stuck in a loop, mapping many different inputs to the exact same, often muddled, output. The team behind PAFM realized that for any intermediate step, there isn't just one correct target, but many plausible ones. By looking at Figure 2, you can see how this works in a simple two-dimensional example. On the left, the standard model creates a mess of points between two moon shapes because it doesn't quite understand the boundaries. In the center, the model trained with PAFM produces a much cleaner result because it considers a whole group of valid targets. Instead of being pushed toward one arbitrary endpoint, the model learns to follow the average direction of many possible outcomes. This is done by calculating an approximate posterior, which basically means weighing multiple candidate targets based on how likely they are. The researchers proved that this approach is mathematically equivalent to the original goals, but with much less noise in the training signal. In practice, this means the AI sees a denser and more coherent set of instructions every time it tries to learn. They tested this new method on massive datasets like ImageNet, which contains millions of categorized photos. Across various model sizes and architectures, PAFM consistently outperformed standard techniques. Specifically, it improved a common quality metric called FID by a significant margin. What is truly impressive is that these improvements come with almost no extra work for the computer. The training process only saw a roughly 6% decrease in speed, which is a small price to pay for much better images. By using a clever trick with nearest neighbors in the data, they can find these multiple targets without heavy calculations. This method also makes the AI much more robust when it has very little data to work with. If you look at the results for sparse data, the PAFM model recovers the true shape of the data far better than the old way. This happens because the model aggregates information from many plausible paths rather than just one. Let's recap. Standard AI training is like following a single, thin thread through a maze. PAFM is more like having a wide, brightly lit path that shows you all the possible ways to reach your destination. This reduces the variance in the learning process, meaning the AI doesn't get confused as easily. Looking forward, this technique could make generative AI much more stable and reliable for real-world tasks. It might lead to AI that needs less data to reach high levels of creativity and precision. Thank you for watching Summarize Science, and stay tuned for more simplified deep dives into complex research.